You would have seen, at least from some of the talks, that the lot of concepts that are required are not exactly what we do in CRT type of a course, but some examples more from really chemical engineering examples are the ones that you would have probably seen as related to what we are doing in CRT. So hopefully you would have gotten you know a flavor for both sides of the spectrum. Two different ends of the spectrum, one where we are looking at more molecular level and more from materials viewpoint and so on. That's where a lot of challenges are. So those are not exactly what we cover in a course like this, but again, you would have probably seen that the reactors are much more complex than simple CSTR, PFRs, and people do things like CFD and detailed analysis to look at the reactors. When it comes to mechanisms, I don't know that you would have seen again from several talks, whether it's experimental talk or simulation talk, the mechanisms will involve so many reactions, not just A going to B, but a lot of intermediates and so on, right? And some of you maybe, I don't know, you would have noticed that if you look at your quiz or the midterm exam, so the reaction that was in the midterm exam, the rate limiting step involved 3 species, right? So you got in the denominator, you would have got something to the power 3, remember? Okay, that's not exactly the actual mechanism how it takes place. The mechanism is a lot more complex than that, and one of the speakers was talking about the exact same reaction, right? You noticed that, right? Oh, no, probably not. You are outside sometimes, sitting outside, so yeah, you may not have noticed. The reason why I'm saying is that some of you have asked the relevance of the things that we do in the class. So just wanted to tell you that those of you who would have attended the CARE symposium would have realized that there is a lot of relevance for the things that we do in the class. It's just that the realistic situations have been simplified to fit the requirements of a course, one. And second, when it comes to mechanisms, we have not looked at selectivity and so on. We have just considered A going to A plus B going to P plus Q. We have not really considered the case where multiple reactions can take place and then a mechanism becomes complex. We have not considered cases like that. When it comes to internal mass transfer limitations and so on, we assume that somehow R actual is known. If you would have seen the presentation from one of the presenters from the industry, from BASF, we would have known that you don't know R actual. You can only measure R observed, and then you don't use actually the Thiele modulus. You actually use an equivalent criteria called the Weiss-Prater criteria. So if you go and look at chapter 3 of Froment and Bischoff, it talks about the Weiss-Prater, WEISZ, Weiss-Prater PRATER criteria. So those Weiss-Prater criteria is something that we actually use in industry as well as in academia. And just a few days back, we were looking at one of the cases where the experimental data did not make any sense. We went back and looked at the Weiss-Prater criteria, and we realized that the reason why it did not make sense, that it started off with a kinetically controlled regime, then went to internal mass diffusion limited regime, and then it went to external mass diffusion limited regime. So in the temperature zone from 100 degrees Celsius to 600 degrees Celsius, I don't remember what was the range of experiments that he performed, but in that range you went from at lower temperature regime, it was kinetically controlled. Why? Because rate of reaction was slow, rate of diffusion was faster than rate of reaction. As you increase the temperature, because of Arrhenius dependence, the rate of reaction increased faster than the rate of diffusion, and then it became internal diffusion controlled because it was controlled by the Knudsen diffusion. And thereafter, when the temperature was increased further, the internal diffusion was both Knudsen plus molecular diffusion, and then external diffusion also became limiting, and then you had the range. So it was kinetic, internal diffusion, and internal plus external diffusion. And how do you come to know all of this? Through an equivalent criteria as Thiele modulus. It's called the Weisbreder criteria. We didn't go over it. It's a very valuable criterion, but it's if you know Thiele modulus, you should be able to read about Weisbreder, and it's not just useful for say catalysis, but let's say you are looking at biomass gasification type of stuff, it will be useful over there. If you are looking at electrocatalysis also, it will be useful over there. If you are working in some of the labs, so if you are working in Arvind's lab, then you will see that the lot of times they will work with powders, and then you will use powders converted into slurry and then do spin coating or dip coating. And the reason to do that rather than to use larger size particles is essentially this: to avoid mass transfer limited regimes. I mean, chemists, what do they look at is basically they rely on their prior experience. As chemical engineers, what do we look at? We have some of these theoretical tools also at our disposal that we can use. So if, for example, you are in a mass transfer limited regime and then you try to analyze the mechanism of reaction, you are not going to get correct results because your kinetics will get affected by mass transfer. Okay, that's a very real problem. That's something that we face in the lab all the time. Every time you submit a paper, one of the questions that get asked, so we put it in supplementary information most of the time, is how do you know that what you are measuring are true rather than are observed. Okay, so that's from a reaction viewpoint. Okay, so this is what we had done last week, and then we talk about flux matching, where we need to get rid of basically the concentrations, which is CAC or CAS and CAS2 and so on. And the way we do that, and that came to one of the questions that one of you had asked, is if you have a slab, what is the net rate of reaction in terms of moles per time equal to? Is it equal to the mass flux? Is it equal to integral of the individual rates, or is it equal to eta multiplied by R rate of reaction into the volume? And I had given a fairly long winded answer to say all of the above, depends on the situation. Okay, and we then talked about a made up example of someone passing food from kitchen to you, and we eating a part of that food before passing out the thali to the next set of people, right? So if we are not consuming any food, then the net food that comes into thali from this boundary is exactly equal to the net food that goes out from this boundary. And let's say if there are 10 windows over here, 5 windows over here, then it's not the flux that will be equal, but it is flux multiplied by 10 windows will be equal to flux multiplied by 5 windows. If that's not the case, then there will be accumulation of thalis in this room, but we have said that there is no accumulation of thali, either thali in the room or accumulation of food in our stomachs. So therefore, those mass or moles in per unit time will match moles out per unit time. But in the case where different rows over here are eating some parts of the food as the food is being passed on, then the number of thalis that are going to come in minus number of thalis of the food that is going to come in minus food that is going to go out will be equal to food that is consumed over here, and that food that is consumed over here is that integral, which is exactly equal to food in minus food out. And if there is no food out going, that is the usual case where we talk about spherical pellet or a slab pellet, where at the center we used boundary condition to be symmetry boundary condition, okay, or dc by dz equal to 0 or dc by dr equal to 0 boundary condition, in which case it is like no food is going out. So, whatever food comes in is being consumed over here. In that case, flux in will be equal to the integral of food consumed, and we have used that in order to compute our eta, and therefore, eta multiplied by kCa is something that you will use at the reactor level, versus the flux matching is what you will use for deriving the equations. Okay, that is where we stopped last week. Okay. So, just to recap, I mean putting it all together for a shrinking core model, this is going to be one question in your assignment. Okay. So, the question that we are going to ask you in your assignment is, let us say there is an external shell and let us say there is an internal core. So, the reaction would be so Qs will be present, and then we are assuming that the size of the particle does not change, it is just that the reacting solid keeps shrinking, and that is why it is called the shrinking core model. The particle remains the same, but the core keeps shrinking. So, it is called shrinking core model, also called as core and shell model. The middle part is the core and the annular part is the shell. Okay. So, what the problem is going to constitute is, let us say if there was external diffusion resistance and there was mass transfer through the shell and then reaction taking place on the surface of the unreacted core, what you are going to have is CAC. Earlier I had called this as CAS2, either one is fine. Okay. This radius is RC, this radius is RS. Okay. If the rate of reaction is K dash CAC, on the surface of this core, what is going to be the net rate of reaction in terms of moles per second into the area? Okay. So, what is the area? RC squared. Yeah, the middle one is RC. Yeah. So, that is meter square, this gets cancelled. Okay. This is the amount of food that is disappearing inside the pellet. Now, food is the gas, okay. Your tummy is getting filled is the solid. Okay. So, you are the solid, the food is the gas, keep that in mind, right. Okay. What about the flux that comes in over here? what is that going to be equal to? Flux in terms of moles per meter square per second. Diffusive flux. Yeah, kg into, so it will be okay. This is in terms of moles per meter square per second. What's the surface area? 4 pi rs squared. Okay. This is this guy, this is this guy. Where does this come in? The first one was limitation through the gas film. The last one was reaction on the core. But now there is diffusion that is taking place through the shell. Okay. The rate of diffusion through the shell is what is going to matter. Okay. Now, what is, so now think of that shell, the red and blue. So, red outer, blue inner, let that middle blue disappear, let the gas disappear. So, think only about this annular part. Okay. At any location, what is going to be the overall model if no reaction is taking place? It is going to be d del square C equal to 0, because no reaction is taking place. Okay. So, you can solve d del square C equal to 0, okay, which is going to basically lead you to dC by dr equal to some constant multiplied by or divided by r squared or r to the power 1. Where does r come in? Because this is a sphere, so the definition of del squared. Okay. You can very well do it like a shell balance, but you can do it in a more consistent manner by a bottom down approach. Okay. But if it was Cartesian, this is going to be what if it is sphere? Okay. This is what I want you to do yourself as a part of the assignment. Okay. 1 by r square d by dr, r square dc by dr, remember long time back. Okay. And when you do shell balances, you would realize that as the area of, so if you think of this particular annulus, area over here is different than area over here. So, the flux through the red boundary is going to be less than the flux through the blue boundary. Okay. As kids you might, or maybe as adults also, you might have played with water hose, right. You take a water hose, you turn on water, what happens? Water is falling slowly. You squeeze the water and the water passes fast, okay, and then you spray your friends with it, right. You have done that or seen that, right. Why does that happen? In first case, this was the surface area through which water was flowing. In second case, you have, let us say, reduce the surface area to say 1/5 of the original surface area. Same volume of water is still flowing through the pipe, okay, but the velocity has increased. Why? Because the area has reduced. velocity multiplied by mass is, or multiplied by moles, is molar flux. So, if you think of molar flux of water, by reducing the area, the molar flux of water has increased. Why? Because this tube cannot hold any more water than whatever water was earlier present. So, the water started flowing. When you held that finger, no more additional water can be stored over here. So, whatever water was coming in is equal to water going out. Over here water is coming at a lower velocity, over here water is going out at a higher velocity, or water is coming out of a lower flux, water is going out at a higher flux. Okay. The idea is same. Here the area was restricted artificially by you by putting a finger. In the other case, the blue area is smaller because it's a sphere. As the radius shrinks, that area also shrinks. So, therefore, the flux increases. Fluxes are not matched, that is what I talked about 10 minutes back. It is the total flow that is matched, that is flux multiplied by area. Okay. What Fogler's book or Levenspol's book or Schmidt's book does, it takes shell balances and says that flux multiplied by area through the red is equal to flux multiplied by area through the blue. What instead we have done is, we have said we have spent 1 week right in the beginning of the course deriving, or not necessarily deriving, but rationalizing this equation. Okay. We have spent last 2 weeks saying how the dC by dt term, how del u del c term and how Ra term drop out for a non-reacting shell. We are just using that and using the calculus, which you should have probably learned. If not, it's a very quick thing to learn now. Even if you are non-engineering background, it's not that tough. It's not easy, but it's not that tough also. It requires you to spend a few hours with it. If you spend that, you will see that all of these are equivalent. Okay. So, you can use CRE module 1 and module 5 concepts with what Professor Pushpavanam is teaching you to derive that exact same thing. Okay. And why do I keep coming back to this? I know it's boring and painful for you to hear, but why I keep coming back to this is, when you go out in a core job outside, or when you are doing your MTech or MS or PhD, okay, it's the ability to take things from one course and another course and the third course and put it together in order to solve that problem. That is what the value of a postgraduate education is, and that is why I will bore you a lot by repeating the same things. It is not that the derivations are different, it is just that we are trying to do that in a different manner. So, what if it is a sphere? It is up to you to derive. Okay. You will get dC by dr is equal to constant multiplied by r to the power alpha, where alpha will be either 1 or 2 or -1 or -2, you can look that up. When you solve that, you are going to get an expression for how concentration changes with R. Okay. Now, how much of your A is coming inside the red? It is going to be d multiplied by dC by dr. You already have dC by dr, it is that constant. Okay. All that you have to do is plug in that constant in that equation multiplied by d. As soon as you do that, this circled expression is what you will get. Okay. Why there is r on the top, why there is r square on the top and r minus r on the bottom has gotten to do with the spherical coordinates and the fact that the outer surface area is lower than the inner surface area. Okay. It is a relatively straightforward math. It just first integral I have almost done, second integral you can do it, apply the boundary conditions and then do that elimination. Okay. Now, you have two equations and two unknowns. What are the two unknowns? CAS and CAC. You know CAB, okay. You have measured CAB, that is the assumption over here. Okay. Use equation 1 and 2 to get rid of use equation 2 and 3 to get rid of CAC, and then use equation 1 and 2 to get rid of CAS. When you do that, the bottom expression, this expression is what you will get. Okay. Now, this has a beautiful way that this expression is kind of gets derived. Okay. You have the numerator, which is kind of rate of reaction. Okay. You have denominator, which is resistance 1 plus resistance 2 plus resistance 3. Resistance 1 is the resistance in the gas. Resistance 2 is the resistance in the shell. Resistance 3 is resistance because of rate of reaction. Okay. What if the reaction was taking place inside that blue core, not just on the surface of the blue core? K dash multiplied by Ca will get replaced by eta multiplied by K dash multiplied by Ca. Okay, or rather eta multiplied by K multiplied by Ca multiplied by A by V. That is what it will get replaced by. Okay, that is something that we are not going to do. I had told you earlier that we won't do, but in case in your research you come across that, that is how you are going to handle it. Okay, and you won't necessarily come across it in just a shrinking core model. Any type of a reaction that involves AS going to QS or BF going to QS, you are going to encounter this. Even in deposition type of reactions, you will encounter this. Okay. Deposition is form quite important reactions in semiconductor industry, microelectronic industries. Okay. And one of the important things when you etch those semiconductors, or not etch, when you when you make deposition. So, for example, you might deposit gallium arsenide on your silicon wafer. When you do that, you want to etch those cases in as vertical walls as possible, and because of diffusional resistances, you won't have that entire thing deposited as vertical wall, but it gets deposited as a non-vertical wall. Okay. That was what was limiting 10 years back, and that was limiting the feature sizes in microelectronics. And today we have got much more precise control over how we do this deposition, how we do this etching, which allows us to go to smaller and smaller feature sizes. That has been the role of chemical engineers in microelectronics. Okay. Companies like Intel and AMD, which you have heard of, and other companies which you have not heard of, like Foxconn and so on, perhaps you have heard of them also. They hire chemical engineers a lot, and they hire you for your ability to understand reactions in presence of mass transfer. Just that in a different context than shrinking core, it is just a growing pattern on the microelectronics. Okay. So, just in case you are wondering, is the relevance only for the reactions that we have talked about? Right, in the beginning of this module we talked about a few reactions or a few cases, right. This was one of the cases that we did not talk about, where all of the concepts from this course, from this module of the course are used. Okay. Yeah, so this I think is something that I just discussed over here. Okay. And elimination to get this is something that so this was, I think last year it was a tutorial problem or assignment problem, I do not know, but this year it will be assignment problem. Okay, this is actually a solved problem in your various stuff, so it is not a huge deal in order to solve this. Okay. So, this is part of the work done. Okay. So far when we had Ag plus Bs, okay, we have talked about how A changes and how the reaction rate changes. Okay. What we did last week in the TA run module, okay, is I took up a case is equal to RB, right, which is minus 1 multiplied by R, right. this is what you would have done. Okay, lot of times your RB was given to you. Okay, in this case, for example, if rate of reaction does not depend on concentration of B, it just happens to be 0th order in concentration of B, has a dependence on concentration of A. Okay, otherwise it might have a dependence on concentration of B as well, depends on the situation. Okay, so this is what this expression is going to be. All you need to do is, how is CB where R basically goes from 0 to Rs. Okay. Okay. And what is CB equal to? CB is equal to NB divided by volume, or rho B multiplied by okay, or whichever the case might be able to do that. All we need to do is substitute this. So, in the dissolution model that you did in the tutorial, what did we say is, as the size changes, the amount of material that is present over there is reducing. Okay. So, let us say that NB is the number of moles at any point of time. Okay. NB is directly nothing but concentration of B multiplied by volume, which is nothing but rho B divided by MB multiplied by pi r cubed. Okay. And dNB by dt okay. If rho and MB are constant, then 4 pi rho B by MB multiplied by r squared is what you will get, and that is how the radius changes as this thing gets dissolved. What happens when it, in case of the shrinking core model? Same thing, the left hand side, notice, does not change. Okay. It is only the right hand side that is now different. Earlier, what was the right hand side? In the dissolution model that you did in your tutorial, the right hand side was just K multiplied by reaction. If it was 0th order, it was just K. If it is first order in A, K multiplied by Ca. If it is first order in A, first order in B, K multiplied by Ca multiplied by Cb. Okay, whatever the case might be. If it is external mass transfer limited, it is Kg multiplied by Cab minus Cas. Okay. So, those were all of the cases that we considered. Okay. The right hand side differed based on whether it is a dissolution or whether it is diffusion or what is the limiting thing. Left hand side remained the same. Okay. Likewise, the left hand side is going to remain the same in your shrinking core model also, but with a small difference. In last week's cases, your particle itself was shrinking. In this case, the particle remains the same, but the core is shrinking. So, last week it was dr by dt. This week, or in your assignment, it is going to be drc by dt. Okay. Examples, if there is coke deposition in the particle, then you are decoking the particle. Example number 2 is let us say your coal, for example Indian coal has more than 40% of ash. As the coal burns, and if the ash does not get removed from the particle, the overall coal particle remains, the size remains the same, it is just that the reacting core keeps shrinking. Okay. That would be another example. Other examples are, whenever you have for example corrosion that is happening. So, as oxide shell forms, your core keeps getting shrunk, but your oxide shell remains oxidized shell remains the same. Okay. And in our catalysis, we see a similar thing is when we look at chemical looping catalysis. So, that means basically we have, let us say bismuth molybdate catalyst. So, it is BiMO and OX. Okay. So, you have oxygen that gets being released because of the oxidation reaction, and that core keeps shrinking. Thereafter, next cycle we pass oxygen on top of it, and from outwards towards in, the bismuth molybdenum starts getting oxidized to form bismuth molybdate. Okay. So, again oxidation cycle you have shrinking core model, or in reduction cycle you have shrinking core model. In oxidation cycle, the core is the reduced catalyst. In the reduction cycle, the core is the oxidized catalyst, but again same concepts. Okay. So, in that case you have reversible reaction, A plus B giving P plus Q. So, in oxidation it is A plus B giving P plus Q, in reduction it is P plus Q giving A plus B, and you keep doing this in a cyclic manner. Okay. So, this is one of the things that chemical looping reactions are one of the things that people are beginning to use in order to address the issue of over oxidation and improving the efficiency in catalysts, and thereby address the problem of CO2 emissions. It is very useful in making ethylene and propylene. Today ethylene and propylene is made through cracking reactions. Gas cracking or fluid FCC reactions are carried out at much higher temperatures than this oxidative dehydrogenation reactions. Okay. Yeah. And again problems to think about, how do you modify the analysis and all, that's fine. Solid dissolution model, putting it together, which is something that you have done in the tutorials last week. Okay. So, that brings me to the end of module 6. Okay.